Today I will take up the topic magnetic effect of current electricity. You know, history of science is replete with examples of what we call accidental discoveries, some of which have given birth to technologies which have improved remarkably the quality of our life. And one such accidental discovery in physics is the magnetic effect of current electricity. It was made by a Danish professor named Hans Christian Ørsted in 1820. He found that when a current is in a conductor, there is a magnetic field generated. A current carrying conductor generates a magnetic field which is found to be reversed when the direction of the current in the conductor is reversed. In fact, till then, it was believed that there is absolutely no connection between electricity and magnetism. And they try to explain electric forces in terms of electric field, magnetic forces in terms of magnetic field, and they considered electric charges to be the sources of electric field and magnetic poles to be the sources of magnetic field, although till today nobody has been able to observe what we call isolated magnetic poles or magnetic monopoles. This Ørsted discovery led to a great simplification, remember it. It showed that nature is economical. Nature doesn't have two separate sources for electric and magnetic phenomena. It has only one source, electric charges. Set the charges at rest, you have what we call electrostatic field or electric field. Set the charges in motion in space, there is both electric and magnetic field. Therefore, we can consider electric field and magnetic field to be two special cases of a more general field, which is what we today call electromagnetic field. In fact, it is the interaction of magnetic fields that is responsible for the working of motors, meters, loudspeakers, tape recorders, and a host of electrical and electronic appliances. If you have a wire carrying current, there is a magnetic field around it. Can you guess the reason why there is no electric field around it? So, moving charges can produce an electric field. Yes, the current carrying conductor is electrically neutral there. Okay. Now, magnetic field is a vector quantity. It has both magnitude as well as direction. To find the direction of the magnetic field, we have a few empirical rules. One is what we call Maxwell's corkscrew rule. Another is Ampere's swimming rule. You can find these rules from any physics textbook. The rule that I am going to use is right hand thumb rule. What the rule says is clasp the conductor in the right hand with the thumb in the direction of the conventional current. The fingers will encircle the wire in the direction of field lines or in the direction of the magnetic field. We will use this rule to find the direction of the field in different situations. If the conductor is not insulated from you, for heaven's sake, don't grasp the conductor. The next day may be declared a holiday in your school, remember it. The shock that you get may be fatal enough. Imagine doing so. Okay, I have two conductors, straight conductors carrying current. These are kept parallel to each other. Let's suppose they carry current I1, I2, and let's suppose I1 is greater than I2. Now, I mark three regions here. Tell me in which of these three regions the magnetic field could be 0? In which of these three regions the resultant magnetic field could be 0? Think about it. Or consider another situation. I have two long straight conductors kept perpendicular to each other but not touching each other. One carries a current in this direction, another carries a current in this direction. Among these four quadrants, in which quadrants the resultant field could be 0? I want you to get me the answer. What do you do? Make use of right hand thumb rule. Make use of right hand thumb rule. In this case, can you tell me in which direction you can expect the field to be 0? In region 2. Here, in which quadrants the resultant field could be 0? No. In no quadrant the field can be 0. Think about it. I'll go to the next idea. Now, if the conductor carrying current is kept perpendicular to the plane of the board, say, this is the cross section of the conductor carrying current, say. You know, if you apply right hand rule, you can show that the field lines are all concentric circles. But how to mark the direction? For that we make use of a notation. If the current is directed into the board, we put a cross mark there. Okay? This shows the current is directed into the board, remember it. That's the rear end of an arrow, you see. How the field lines will be? They will be, am I correct? Whereas, if the current is coming out, this is the tip of an arrow, current is coming out. Here also you find that concentric circles. Make use of the right hand rule to mark the direction of the field around that. Okay. Now, suppose you have two conductors separated by a distance r, say, kept perpendicular to the plane of the board. One carries a current into, another carries out of, and both these carry equal currents, say. I am interested in finding what is the direction of the resultant magnetic field at this point P, say, which is at a distance r from both these conductors. Suppose I mark these directions, say PA, PB, PC, PD. Work it out yourself. Use your right hand thumb rule and find out along which direction among PA, PB, PC, PD the resultant field is oriented. The earlier one that I rubbed it off. 1 and 3 is the answer. Oh, that's the wrong answer. Only 4? 2 and 4 is the right answer. Yes. Now coming to another problem. I have 4 conductors kept at the 4 corners of a square, say A, B, C, D. Current coming out here, current coming out, current into, current into. These are the sides of the square. Use your right hand rule to find the direction of the resultant field at the point over there. use your right hand rule to find the direction of the resultant field at the point O there. Okay. We have been dealing with the direction, but we are also interested to find the magnitude of the magnetic field. The discovery of this magnetic effect by Ørsted was actually announced in the month of September in 1820, and within a few weeks, Biot and Savart gave us the equation to find the magnitude of the magnetic field produced by a current carrying conductor. Suppose you have a conductor carrying current I, and if you are asked to find, say, the magnetic field at some point P, the conductor is kept in free space. What the rule says is, break this into a very large number of very small pieces, each piece of length dl. Okay. Please don't break it physically, because in that case no current can flow through it, remember it. Imagine doing so. Consider one such element AB, say of length dl, which is at a distance r from the point P. With every element dl, associate a direction, that is the direction of current in that. That is the direction of current in that. Then consider a vector IDL, which has a magnitude which is equal to the product of strength of the current and the length of the element, and direction, the direction of the current in the dl. We call this current element. We call this current element. Consider a unit vector along the direction joining the element and the point P. Let theta be the angle between these two vectors. Theta be the angle between those two vectors. Then Biot-Savart law says the magnetic field produced by this current element AB is given, its magnitude is given by dB is equal to mu naught by 4 pi I dl sine theta by r squared, where mu naught is what we call permeability of free space, which has a value mu naught equal to 4 pi into 10 to the power minus 7 Henry per meter. When I is in amp, dl are in meters, dB is in Tesla, that's the SI unit of magnetic field, remember it. dB is in Tesla. This holds good for a point in free space, remember it. This can be put in the vector form as vector dB is equal to mu naught by 4 pi I dl cross r by r cubed. Remember, this is the field produced by an infinitesimal element. This cannot be verified in your laboratory by doing an experiment, because we don't consider or we don't deal with all elements in our experiments. We have a circuit, you see, in which a current is flowing. But what results we get, they have been found to be true actually. Now, what is the field at P produced by the entire conductor? As we have seen in the case of, electric field, you can make use of the principle of superposition, so that by integrating this expression over proper limits, you can get the resultant or the total field. But you have to be careful here on one count. What is that? In the case of electrostatic field, the source of electrostatic field is electric charge, which is a scalar quantity, whereas the source of magnetic field is a current element, which is a vector quantity. Remember it. That is, you have to be careful about. Clear? Now, we will use this, or we will apply this Biot-Savart's law to find the magnetic field in different situations. We will start with the simplest case. I have a thin wire of length L bent in the shape of an arc of a circle of radius r, of radius r, subtending an angle phi at the center of curvature. What is the strength of the magnetic field produced by that? What we do is take a small element of length dl, take a small element of length dl, find the field that this produces at C. That is given by, the magnitude is given by mu naught by 4 pi I dl sin theta by r squared. Okay. Now, what is the value of theta? Wherever you choose this dl, you are choosing it along the length of an arc of a circle, and the angle theta is now nothing but the angle between the tangent at that point with the radius, which is always for a circle 90 degrees, sin 90 is 1. So that this you can write it as mu naught by 4 pi I dl by r square. So what is the total field? Integrate this, which is mu naught by 4 pi I by r square. This dl is r d phi, will you agree? We integrate it from 0 to phi, say, you can get it as mu naught by 4 pi I by r, because one r cancels, integral d phi is phi. So this is the expression for the field that you get produced by a arc of length L at the center of curvature. Now, when you substitute the given quantities in this, you have to be careful about one particular quantity there. What is that? What is that? Can you guess? You have to be careful about one particular quantity when you make a substitution there. You have to be careful about the quantity phi. Can you guess what you need to take care of? Phi should be in radians. Never forget that. Phi should be in radians. Now, you can use this to find the field at the center of a circular loop carrying current. At the center of a loop carrying current, it carries a current I, say. What is the field at the center? Let's suppose the radius is r. Of course, we take it to be an ideal loop. Okay. First, what is the direction of the field? You know, right hand rule. Right hand rule. Correct now? It is directed perpendicular to the plane of the coil into the board, isn't it? There is another interesting rule which gives you the direction. It's called right hand palm rule. It says, hold this coil with these fingers in the direction of the current, then thumb will give you the direction of the field. If the current flows in the anti-clockwise direction, you can imagine The field again is perpendicular to the plane of the coil, but directed towards the observer. Okay, that's about the direction. What about the strength of the field, or magnitude of the field? What you need to do? You substitute for phi, what angle? 2 pi, exactly. So it is mu naught I by 4 pi, 2 pi by r. As you can see, it is mu naught I by 2r. See, so simple a derivation. Sir, if there are n turns in the coil, how do you go about? Into n. If there are n turns in the coil, this is into n. This is what you get. Okay, let's apply this result to arrive at the expression for the field at the center of X, a spiral. I have a wire wound in the form of a spiral, say. It carries a current I. The spiral has an inner radius, or radius of the innermost turn A, outermost turn B. It carries a current. Tell me how to find the field at the center of the spiral. How to find the field at the center of the spiral. I'll give you the hint. Use this result. How do you do this? How do you do this? Tell me. Come on. Mu naught I by? In by 2. Into 1 by A plus 1 by. No. I can't accept that. What you do is consider a radial element of width dr between the radii r and r plus dr. Consider a radial element of width dr, okay, between r and r plus dr. Can you tell me what is the number of turns in that? Number of turns in the element of width dr. Can you tell me how much it is? Come on. NDR. Capital N is the total number of turns that I have given. You are asked to find what is the number of turns in this width dr. I will call it as dn, say. How much it is?
B minus A by.
No. N divided by B minus A gives you what? N is the total number of turns spread over a distance B minus A. So, number of turns per unit distance, radial distance, is multiply it by, clear? Therefore, field produced by those many turns at the center is mu naught by 2 pi, mu naught I by 2, mu naught I by 2 mu naught I by 2 r into dn, which is mu naught I by 2 n dr B minus A into R. Will you agree? This is the field produced by those many turns, correct now? Spread over a radial distance dr. Therefore, what is the total field? Integrate this from where to where? From A to B, mu naught I n dr by 2B minus A into R. You can take this mu naught I n by 2B minus A out of the integral sign A to B dr by R. What is dr by R? So, B is mu naught Ni by 2B minus A log B by A to the base. Okay, I have a circular coil carrying a current, say 2 amps. Let's suppose the radius of this coil is say 10 centimeters. It carries a current. The current comes from a wire. It is attached at the end of one diameter and it flows out through a wire attached at the other end of the same diameter. Okay, the question is, what is the strength of the magnetic field at this center wall? What is the strength of the magnetic field at the center wall? Think about it. Direction you can find with the right hand thumb rule. Magnitude you can find with the equation that we have already derived. Therefore, you can know what is the strength of the field at the center. Now, we will take up a more general case to find the field, for example, at any point on the axis of a circular coil carrying current. Suppose this is a circular coil of radius r. It carries a current I am sec. This is the center of the coil sec. You are asked to find what is the field at a point P on the axis at a distance x from the center. Remember, I have kept the coil with its plane perpendicular to the plane of the board such that axis lies on the board, remember. What you do is take an element, I will call it Mn, say of length dr, which is at a distance, say, capital R from P, which is at a distance capital R from P. Let me call this angle some phi, say. What is the field that this current element produces at P? Come on. dB is equal to mu naught I by 4 pi dl sin theta. That's what Biot-Savart law says. What is theta here? Angle between the direction of the current, that's the direction of the current element, and the line joining the element and the point. The current is coming out of the plane of the board, whereas the line joining the element and the point, it's in the plane of the board. So theta should be sin 90 is, so this is mu I dl by 4 pi. Remember, sorry, by r square. Field is a vector quantity, remember it. This field therefore is directed along a direction perpendicular to the line joining the element and the point. It's in the plane of the board, but perpendicular to the line joining the element and the point. Do you agree? Now, suppose you draw a perpendicular to this axis. Choose this as the x-axis and choose this as the y-axis. You can see this angle should be phi, because this line is perpendicular to this line is perpendicular to this line. Angle between any two lines is equal to angle between the perpendiculars to those two lines. So, this dB can be resolved into dB cos alpha perpendicular to the axis and dB sin alpha along the, dB cos phi, dB cos phi, dB sin phi along the axis. Will you agree? Now, for every element that you choose here, there exists a diametrically opposite element at the same distance r, okay, which produces a field dB dash equal in magnitude to dB, which can also be resolved into dB dash cos alpha and dB dash sin alpha. As you can see, cos components being equal in magnitude and opposite in direction, they cancel off. What we are left with is only sin components, so that resultant field at P is summation of dB sin phi. This is mu naught integral of mu naught I dl by 4 pi r squared. Sin phi is opposite side by hypotenuse, or this you can write it as, I am integrating it over 2 pi r. Will it be all right now? Mu naught I r by 4 pi r cube, integral dr is 2 pi r, correct? Integral dl is L, upper limit is 2 pi r. So, this is mu naught by 4 pi 2 pi r squared I. What is r cubed here? You can link it to r squared is small r squared plus x squared. So, r is square root of r squared plus x squared. So, r cubed is r squared plus x squared power 3 by 2. This is, remember, for a coil having only one turn. If there are n turns, then it becomes mu naught by 4 pi 2 pi n r squared I by r squared plus x squared power 3 by 2. In fact, from that, you can find the field at the center. How? Tell me, how can you find the field at the center of the coil from that relation? Put x equal to and check whether you get what we proved earlier. Okay? So far, we have considered the field at the center of these circular coils. Suppose you are asked to find the field produced by a straight wire carrying current. How do you go about it? You have a straight wire carrying a current I. You are asked to find what is the field at certain point P, which is at a distance, perpendicular distance r from the wire carrying current. Tell me how you go about. Divide this into a very large number of very small elements. Consider one such element of length dl. You call this element AB, which is at a distance, say r. Call this angle between the direction of the current and the line joining the element and the point as some theta. Let this distance be L, say. Call this angle phi, say. Okay? Now, you can find what is the field at P produced by the current element AB. dB is equal to, what is the magnitude of the field? Direction you can find using right hand thumb rule. You can see that it is directed into the board at P, correct now? What is dB? Mu naught by 4 pi I dl sin theta by r square. Will you agree? Or this you can write it as mu naught by 4 pi I dl by r square. Sin theta can be written as cos phi. Will you agree? Because this is a right angle, theta plus phi is 90 degrees. So theta is 90 minus phi. Sin theta is sin 90 minus phi, which is cos phi. That's what I have written. Therefore, B is equal to integrate this mu naught by 4 pi I dl by r squared cos phi. Of course, you have to reduce it to a one variable. There are so many variables. What you do is, you can see L by R equal to tan theta, so that L is equal to R tan theta. Will you agree? L by R is opposite, tan phi, I'm sorry. L by R equal to tan phi. So dl is equal to R 6 squared phi. Will you agree? Then capital R is equal to small r into what? Capital R equal to small r into small r by capital R is cos phi. Capital R by small r is, will you agree? So here you can write B is equal to mu naught by 4 pi I dl is r sec squared phi d phi into cos phi by r squared is clear? Or you can write this as clear? Okay, suppose you consider the conductor to be infinitely long. If you consider the conductor to be infinitely long, what are the limits of integration that you can put? If you consider the conductor to be infinitely long, for an infinitely long wire, mu naught I by 4 pi r cos phi d phi. What are the limits? Upper limit pi by lower limit minus pi by 2. If you put pi by 2 in both upper as well as lower limits, you get 0 answer. Remember it, it has to be minus pi by 2. So this will be how much? Mu naught I by 4 pi r. Correct now? Cos phi when you integrate is what? Sin phi? Correct now? Sin pi by 2 minus of minus plus sin pi by 2, which is mu naught I by 2 pi r, because so remember, in the case of a straight conductor of infinite length, field is given by this. Clear? Suppose it is of finite length. If it is of finite length, for a conductor of finite length, what is the result that you can put? Come on. For a conductor of finite length, you integrate it from phi 1 to phi 2, so that you can get it as clear? Is it clear? Okay. So far, to calculate the magnetic field, we have considered a conductor carrying current. Now, suppose you are asked, what is the magnetic field produced by a point charge Q which is moving? A point charge Q is moving with a constant velocity V. Of course, this velocity is nothing compared to the speed of light. In such a case, how to find the magnetic field produced by a moving charge, moving with constant velocities? How do you go about? We start with Biot-Savart's law only. Minus of minus phi by 2, which becomes plus. What is that? Upper limit is pi by 2, lower limit is minus pi by 2. You have dB mu naught by 4 pi I dl cross r by r cubed. Okay, this is the field produced by a current element at a point distance r. Our problem here is to find the field at a point distance r from a charge, point charge of strength q, moving with a constant velocity v, say. How do you go about? What is I? I is dq by dt, correct now? So what is I dl? It is dq into dl by dt. Clear? Now, here dq stands for the charge contained in an element of length dl. In the limiting case, okay, In the limiting case, if the entire element contains only one charge of strength Q, then this dq can be written as some q only, in which case you can write it as some qv. Will you agree? So that dB is equal to mu naught by 4 pi I dl is qv cross r by r cube. This is the field produced by a charge moving with a constant velocity. We have calculated the field at the center of a circular coil or at the center of a circular loop. Remember, when a current is there in a circular loop, the charges are actually running along a circle. Circular motion is an accelerated motion. Here you derive this, or even in the Laplace's law, we make an assumption that the charges are moving with constant velocity. But when the charges move in a circular loop to produce a field at the center, they are moving along a circle, means they must be accelerating, no? So, will it not go against the assumption of Biot-Savart? When you calculate the field at the center of a circular coil or of a loop, you expect the charges to accelerate because they are moving in circular path. Circular motion is an accelerated motion, whereas our assumption there is that it is moving with constant velocity. So, is it not contradict? Tell me, what is the explanation that you can offer to this? What is the explanation that you can give? Drift velocity is? Acceleration is here centripetal acceleration, isn't it? What is the expression for centripetal acceleration? V squared by R. Now tell me, what is that V? Drift velocity. Okay. You might have already seen the value of drift velocity. You might have already calculated what is the order of magnitude of drift velocity in ordinary conductors. 10 to the power of minus 4, fraction of a millimeter per second, so that square becomes so small. It becomes so small, so you can neglect it, remember it. Okay. I have an electron moving along a straight line. You know the charge on an electron is 1.6 into 10 to the power minus 19 of a coulomb. It moves with a velocity, say 6 into 10 to the power of 7 meters per second. Okay? At a particular time instant, what field it produces at a point just 5 millimeter away from it along its line of motion. Along its line of motion, just 5 millimeter away from it, what field it produces? Find it out. Next is, what is the field it produces? What is the field it produces 5 millimeters behind it? At any instant, what field it produces 5 millimeters behind it along the line of motion? Next is, what is the field it produces at a particular time instant at a point 5 millimeter, at a point 5 millimeter below its line of motion. 5 millimeter below its line of motion. What answers you get? A, yes. In the first case it is 0 because theta is 0. Exactly. Second case again? 180, 0. Exactly. Then third case? How much you get? Work it out. Anyway, work it out. The next problem, I want you to work it out here itself. Take down the problem. A thin ring of radius 10 centimeter, you can just take down the data and work it out. A thin ring of radius 10 centimeter carries a uniformly distributed charge. Carries a uniformly distributed charge. The ring rotates at a constant speed of 1200 RPM. 1200 RPM, that is 1200 rotations per minute. About its axis passing through the center of the ring. About its axis passing through the center of the ring and perpendicular to its plane. Find the charge carried by the ring if the magnetic induction at the center of the ring is 3.8 into 10 to the power of minus 9 Tesla. I'll give you 60 seconds. Try this and get me the answer. What's the formula that you use here? What's the formula that you use? B is equal to mu naught by 4 pi Q into V by R square. What he has asked is Q, all other things he has given. You may ask, sir, velocity is not given. What you can do? In the place of V, put R omega. In the place of omega, you write 2 pi F. He has given rotations per minute means F, no, it is. Rotations per minute is F. Of course, it has to be converted into rotations per second. Come on, do that calculation and get me the answer. Got the answer? Okay, I'll give you the answer. You take it as homework. Answer is Q is equal to 3 into 10 to the power of minus 5 of a coulomb. Next, take this problem. A circular disc of radius capital R, a circular disc of radius capital R made of an insulator carries a uniformly distributed charge capital Q, carries a uniformly distributed charge capital Q and is rotating with a constant angular speed omega. And is rotating with a constant angular speed omega. Calculate the magnitude of the magnetic field. Calculate the magnitude of the magnetic field at the center of the disk. Calculate the magnitude of the magnetic field at the center of the disk. So this is a disk, circular disk of radius r, he says. It carries a charge q which is uniformly distributed over its surface. Okay. He says it is rotating with a constant angular speed omega. What is the magnitude of the magnetic field it produces at the center? Can you tell me how to attack this? One of you. I'll give you the hint. You use this relay. Consider a
point
Mm.
at a distance r from the center.
Mm.
Then you know its velocity as omega r.
Mm.
And then you can find the effective charge at that point.
At a point, this charge is,
The circular ring.
that means you consider an element of thickness dr and radius r. Find the area of the element. Okay. You know the charge per unit area, that is surface charge density. Multiply that area by the surface charge density, that is the charge residing on that. That charge you can take it as equal to dq. So mu naught by 4 pi dq by r squared into v. V is r omega. Correct now? That is the field produced by that small element. So what is the total field produced by the entire disk integrated from 0 to capital R? Come on, do that and get me the answer. What is the answer you get? Area of the element that you have chosen. What is that, man? 2 pi r dr. Charge residing on the element, how much? dq is equal to 2 pi r dr into sigma. Sigma is q by pi r squared. Correct now? That is dq. Therefore, what is the field dB produced by this? It is mu naught by 4 pi into dq, which is 2 pi r dr q by pi r squared into v, which is r omega divided by r square. Clear? Integrate this from 0 to r mu naught by 4 pi. So many things cancel there. What is the final answer? Q omega by, yes, that's the answer. That's the answer. Of course, we will see in the next class how to calculate the field at the center of curvature of a charged hemisphere which is rotating, or field at the center of a charged sphere which is rotating, or field along the axial line of a, say, rod which is charged, which is rotating. Various problems can be there in this, remember. We will see those problems in the next class when we have exclusively problem solving session. You know, on every Wednesday we have only problem solving session. Now I go to the next idea. You have a charged particle moving in a magnetic field. When a charged particle moves in a magnetic field, it is found that it experiences a force, and this force is given by the expression F is equal to Q into V cross B. Suppose this is the directional field, this is the direction of its velocity, this angle is theta. This is F equal to Q into V cross B. The direction of F is the same as the direction of the cross product V cross B, you know, which is perpendicular to the plane containing V and B, and it is in the direction in which a right-handed screw would move when rotated from G to B through the acute angle. This is the force that, this is the direction of the force a positive charge would experience. If you consider a negative charge, the magnitude remains the same, but the direction will be in the opposite. Clear? From this, you can say the magnitude of the force is given by QVB sin theta. As you can see there, when Q is equal to 0, force is 0. That means neutral particles do not experience any force when they move through a magnetic field. Neutral atoms, neutral molecules, or neutral particles like neutrons, for example, they don't experience any force when they move through a magnetic field. Then, when V is equal to 0, even if a particle has a charge, if it is at rest in the magnetic field, you don't experience any force. Stationary particles, stationary charged particles in magnetic field won't experience any force. You can expect them. Why is that? A moving charged particle experiences a force in a magnetic field. If the charged particle is at rest, it will have an electric field, but it is not having any magnetic field. Interaction can take place between two magnetic fields or between two electric fields, not between electric field and a magnetic field. When the charged particle is moving, it produces a magnetic field. That magnetic field interacts with the external magnetic field, and that results in the appearance of a force. Clear? Another interesting thing here is, even if Q is not 0, V is not 0, B is not 0, even then F can be 0. When theta equal to 0, or when theta equal to 180 degree. That means when the particle moves in the direction of the field or in a direction opposite to that, it won't experience any force. It experiences a maximum force. It experiences a maximum force which is Q, V, B. That is when theta equal to 90 degree. You see, you had used this equation to define electric field. You had put this as vector E is equal to vector F by Q. Electric field is measured both in magnitude and direction by the force acting on a unit charge, you said. There, the direction of the field is same as the direction of the force. So from this you can get both informations. But here, the direction of the field and the direction of force are not one and same. No, they are totally different directions. So when you use that to define the strength of the field B, remember, first of all, you should know what is the direction of the field. That is the direction in which the particle won't experience any force when it moves through the field, isn't it? So you first find that direction and then use this to find the magnitude. As you can see here, what is the unit of B? Tesla. Unit Tesla is equal to Newton. This is in Coulomb meter per second, or this is Newton by Coulomb per second is ampere, correct now? So you can write it as Newton per ampere meter. Newton per ampere meter, that is Tesla. We will see later when I take up magnetic properties of materials. You know, you defined electric field in terms of number of field lines per unit area. You called it flux density. More the number of lines per unit area, or more the field lines per unit area, stronger is the field. Here also you can define it that way. You can say magnetic flux density, magnetic field, magnetic flux density, magnetic induction, all mean one and same. The SI unit of magnetic flux is Weber. So the SI unit of magnetic flux density must be Weber per square meter. That's Tesla. Tesla is nothing but Weber per square meter. We also use a CGS unit. What do you call it? For magnetic field, the CGS unit is Gauss. Ørsted or Gauss, isn't it? What is the CGS unit of magnetic flux? Anybody knows it? CGS unit of magnetic flux? Maxwell. What is the CGS unit of magnetic flux density? Maxwell per square centimeter, that is Gauss. Weber per square meter is Tesla. So how you can relate these two? One should be equal to 10 to the power of 4 times the other. No, because when you convert from square centimeter to square meter. Clear? So I'll stop at this point.